You have reached the last lab of the quarter. Woohoo! And the purpose of this week's lab is to practice using FSM's, finite state machines, to do some relatively useful stuff. And in the beginning of the quarter, we started with doing a lot of additions, and then we added on subtraction when we learned sign numbers, and now you get to design a multiplier based on an FSM. So the lab first describes how to go about doing a multiply. Instead of using that little star symbol, which is Shift 8 on your keyboard to do a multiply on a computer, you're actually going to implement a multiply by a sequence of adds and shifts. And this is actually how a computer does handle a multiply. Instead of doing a multiplication, it often does a bunch of adds and shifts. Of course, there are a lot more advanced techniques to speed up multiplication nowadays. Anyway, so in the lab you'll see an example here of how to do a multiply in binary based on adds and shifts. So here you can see what we're doing is we're going to be multiplying. In this case, it's a 3-bit by 3-bit multiplication. And your 3-bit by 3-bit multiplication can result in a value that if you add the number of digits in each of the operands, so this is a 3-bit by a 3-bit, you could get up to a 6-bit result. That's just something to keep in mind. So if you do a multiplication of a 3-bit by a 4-bit, you could get up to a 7-bit result. Anyway, so you see we have operand A and operand B. Operand B is sort of used to tell you what you are going to be doing with operand A. So let's start this multiplication. We look at the least significant bit of operand B. Because it's a 0, we're not going to add anything to our result. So our result starts off at 0, and we're not going to add anything to our result. It's going to be all zeros. Then we look at the next bit of operand B, which is a 1. Because this is in the second bit position, or rather the first bit position, if this is the 0th and the first bit, what we're going to do is add a shifted version, shifted over by 1, as you can see here, to the result. So a shifted version of operand A to the total result. So here you go, we're adding the shifted version of operand A to the total result here. Then we move on to the next bit, which is also a 1. So because this bit is in the second position, we're going to shift operand A by 2 and add it to the total result. So here you have the 0 from this 0, the 3 ones from this one, the 3 ones from this one, and you're going to get a result when you add these all up of 42. And guess what? 7 times 6 is 42. So you just implemented this multiplication based on a series of adds and shifts. And the goal for this lab is to turn this into an FSM. So basically you're going to have a bunch of states, and you'll be looking as your input to the least significant bit of your B operand. And whether it's a 1 or a 0, you'll be adding a 0, or you'll be adding a shifted version of operand A. Now let me do another example just to solidify this for you in Excel here. Let's say we're going to multiply two 4-bit numbers. 3 is our A and 11 is going to be our B. And this result is known as an accumulator, and you'll see that word in the lab text. An accumulator is just a memory element that's going to hold or accumulate a value. So just like you'll see in this example, the accumulator will start off at 0 and then it will just keep adding on to itself. You'll also see a term in the lab write-up called register. And register is a very general term used in computers to denote a small memory device. So you can think of a register as just a collection of flip-flops. So you could have an 8-bit register, a 32-bit register, a 64-bit register, etc., etc. And it's, like I just said, it's just a small memory device that holds bits. And in this case, our accumulator is going to be also a register that's just going to hold the results of this multiplication. Okay, so let's go ahead. If we're going to be multiplying 11 times 3, the accumulator starts off at 0. We look at the least significant bit of the B operand, which means that we're going to be adding 3 or 0011 to the accumulator. And the accumulator will now have the value of 3 because we've added 3 to 0. Then we look at the second bit, which is also a 1, which means we're going to add a shifted version of operand A. So this is now a 6, right? 110 is a 6, and that's going to get added to the accumulator. So 3 plus 6 is 9. Then the second bit, or the 0, 1 second bit, is a 0, so we're going to just add 0 to the accumulator. So 9 plus 0 is 9. And then this last bit, this 1, or most significant bit of our B operand, means we need to add a shifted version shifted over by 3 to our total. And this value is a 16 plus an 8, which is a 24. So if we add 24 to our accumulator, 24 plus 9 is going to be 33. And there's our result. So as you can see here, our multiplication of 3 times 11 gives us a 33 after going through all these steps. And you can think of these as different states in your state machine. You start off in the reset state, and then you advance to these different states as you're adding and shifting the operands. So you're going to be creating this finite state machine and this accumulator within the finite state machine. And just to give you a better idea of an accumulator, or how to implement that in VHDL, I've created an accumulator VHDL file to show you. So here is an example of an accumulator, and I don't intend for you to just add an accumulator entity to your finite state machine. You can just incorporate code that looks like this to help you in your FSM to create something that's like an accumulator. So here what I'm doing in my just example accumulator, I have a reset signal, an input A, which is 4 bits, a clock, and an output accumulator, which is my total value. Then I have my temp A signal, and as you can see, all temp A is extending the bits of A to be total of 8 bits, which is going to be my total accumulator value. And notice you've probably used this concatenation operator before, and I just wanted to give you a hint that if you wanted to, say, create shifted versions of A, you can do things like this, concatenated with, 0. So this would also create an 8-bit value of A, but it would be A shifted over by 2 bits. So just keep that in mind if you want to be adding shifted versions of A. Okay, so in my little example here, I've just created temp A to be an 8-bit version of A, and then you can see in my process statement here, I have, if my reset signal is a 1, then I'm going to clear my accumulator. And I'm going to clear this signal, this temporary signal called temp sum. This is the value that is getting added onto itself. Then I have here, else if the rising edge of clock, then my temp sum is going to get itself plus temp A. This is the whole part of the accumulator here, that you're adding your new value onto itself. And as you can see then, I assign temp sum to the output accumulator. So that's how an accumulator works. And if I wanted to see this actually happening on my board, what I could do is I could assign switches to my A input, I could assign a clock value, and I could assign my accumulator output to my 7-segment display so I could see it on the display. And then as I put in switches, every rising clock edge, I'll see that value get added to the accumulated value. Now you might be thinking, wait a minute, that clock goes really fast. So guess what? Like you've also had in your previous experiments, you can add a clock divider. So here you can see in my test accumulator project file, I have added my accumulator, my clock divider, and my 7-segment display, and I put them all into one big top module which port maps all those 3 components. Okay, so that brings me to my next topic of this clock divider. We've been using the clock divider code, but I wanted to, now that you've learned about frequencies and periods that you can actually make this clock divider go at a speed that you so desire. So in this clock divider 2 module, you should be able to understand what's going on right now. What we have going on is at the rising edge of the count, we're checking to see if this count, which we've called div count, is equal to the max count, which we've defined. Here it's defined as 25 million, it looks like, 6 zeros. So if we've reached that count, what we're going to do is flip the signal. Temp clock gets not temp clock, else we're just going to count up. So what you can see is happening here is this signal temp clock starts off at 0, right? Temp clock starts off at 0. So let's say we're going to be counting up from 0 all the way to this max count number, this many, so 25 million rising clock edges of the input clock that comes in. So our input clock is coming in at 50 megahertz, and we're going to have 25 million of those 50 megahertz clock edges counting out while we're outputting a value of 0. Because here where temp clock is going to stay 0 and we're just counting up. Once we get 25 million, we're going to change that signal from a 0 to a 1. Temp clock gets a 1. And then it's going to be a 1 for 25 million cycles of this clock that we're inputting. And so as you can see what's going on, we have temp clock is 0 for 25 million cycles, and then temp clock is 1 for 25 million cycles, and then temp clock is 0 for 25 million cycles, and temp clock is 1 for 25 million cycles. So you're creating this slower clock signal by doing this count. So since we know that if we're low for 25 million cycles and high for 25 million cycles, that means one period of our new clock is going to be 50 million cycles, because we're low for 25 and high for 25. It's going to be 50 million cycles of the original clock. Now, since our original clock is running at 50 megahertz, if we divide that by 50 million, which is 50 mega, guess what? We get 1 hertz. So with this number, we are actually now creating a 1 second period clock, because 1 hertz will give us 1 over 1, a period of 1 second. So you can now, since you know this number affects the clock, you can figure out whatever clock speed you want to get with your new clock. You can modify this number as you see fit to get the speed of the new clock that you want. So in my case, I wanted to be able to, in my accumulator example, be able to see a value getting added to my accumulator every 1 second. So that's why I selected this number of 25 million. Okay, so I'd like to then finish this. Let me just go back to the lab write-up. So this gives you the assignment down here and then gives you some helpful hints. I'm going to end this intro to the lab with a demo on the Nexus board of what your final design should look like. Okay, so here's an example of what your board might look like. You can see on the switches that I have 0011 or 3 as my A input and 1011 or 11 as my B input, and currently I'm showing 0 in my accumulator. When I hit the go button, which is the button right here, you can see that my LEDs show which state I'm in, and as we did in the example in Excel, let me push it again. Kind of weird doing this backwards. It starts off at 0, then it went to 3, then 9, held at 9 because we added 0, and then became 33. So you can see me cycling through the states with the LEDs and the accumulated results on the 7-segment display. And now you can see me. I hope you've had a great quarter, and good luck on your final project.